Perfect. All right, guys. So yeah, so let's start chapter 7. So this is chapter 7. So we're gonna start with, of course, section. Actually, I'm gonna combine. I mean, section 7.1, 7.2. They're kind of similar. So I'm gonna combine them. So we're gonna do section 7.1 and section 7.2. All right. Yeah, so the section 7.1, 7.2, they are about the path integrals of scalar, so scalar and vector line integrals. Okay, so what's the goal of these two sections? Well, guys, I mean, so we know how to integrate, functions of single variable over an interval, right? So, we know how to integrate. So far, we know how to integrate. Well, first, of course, functions of single variable. Right, over an interval. Okay, and we said that the main interpretation would be, so you have your x-axis, you have some interval here, let's say a and b, and then you have some function f of single variable. This is f of x. All right, and so the main interpretation of this integral function of single variable is that it gives you the area bounded by the function f and the x-axis, right? So that's for the functions of single variable. Now, we also know how to integrate, over a region in the plane. So if you have a function of two variables, functions of two variables, right, over a region in the plane. Okay. And so we said, so the main interpretation would be, so we have some, you have your two variables x and y, right? And you have some region in the plane. So let's say this is my region D, right? And we said, I mean, the main interpretation would be of this integral over a region in the plane. So if you integrate the constant function 1 over D, right, that would be equal to the area of the region D. Right. Okay, so that's for functions of two variables. Now for functions of three variables, so we know how to integrate them over, a solid in the space. So, over a solid in the space, right? So you have three variables, x, y, z. This is y, this is x, this is z. You have some solid in the space, some solid here, some solid here, wherever. So this is my solid S. And so if you integrate the triple integral of the constant function 1 over S, right? That will be equal to the volume of S, right? Anyway, so what I'm saying, guys, is that we know how to integrate over an interval, okay, over a region in the plane, and over a solid in the space, right? A solid in the space. So today we're gonna see how to. So today we're gonna see how to integrate over or along a curve or a path in the space. So today, so we're gonna try to see how. So how do we integrate along a curve? So what do I mean by curve here? I'm going to define later in a couple of minutes a curve. So a curve or a path. Okay. Curve in the space. In the space, or in actually, or in the plane. Okay. So yeah, so we're gonna learn how to integrate along a curve, right? So along a curve, right? So we know how to integrate over an interval, over a region, over solid. So today we're going to see how to integrate along a curve, right? Now, so let me first define what do I mean by curve, right, or a path in the space. Okay, so probably you have seen this in Calc 3, but let me just remind you here the definition of a path or a curve in space. So what's a path or curve? So what's a curve? Path in the space. Okay, so the definition of a curve, or path, or curve is that it's actually a function. So a path, say gamma in the space, is actually a function. Okay, it's a function. Well, it's a function gamma. Okay, of course, this is gamma. This is a Greek letter, right? This is gamma. Okay. I mean, gamma is like the common notation for paths or curves in the space. Anyway, so gamma is a function from an interval. So from an interval AB to R3. So R3 again is the space. So we have this function from this interval AB to the space. So gamma of t. So the variable here is t. So t belongs to the interval AB, right? So t so belongs to the interval AB. So gamma of t is equal to let's say first function here. So it's an R3, right? In R3 we need the three components, right? So first component is given by some function of t. Let's call it x of t. Second component is given by y of t, right? And the third component, this is third function, is given by some function z of t. Okay. So the idea, guys, I mean, behind this, I mean, the idea of path in the space is the following. So, so you have this interval AB, right? You have this interval AB. Okay, and so your variable t is in the interval AB. So you should think of t as like, let's say, a time. Okay, so just think of t as a time. right? And here, so we have this function gamma. It goes from this interval AB to the space. So here's my space. This is my x-axis, y-axis, and z-axis, right? So the idea is, for each time t, you associate a point in the space, right? So let's say here, this is a, right? So here, t is equal to a, okay? So using gamma, you associate to the time t equals to a some point in this space. So this is the image of a. So this is, let's say, gamma of a. Okay. And then you have another time t here somewhere between a and b. So you associate to this point in the interval ab, another point in the space, okay, etc. And then in the last point in the interval, that's b, right? This is a t is equal to b, right? And so the image of b by the function gamma is going to be some point here. This is gamma of b, right? So we're going to have like a bunch of points. So if you connect all these points, you get your, you get your path or curve in the space. All right. So so this is what I call a path or a curve in the space, right? So this curve or path, it doesn't have to be like a straight line. It could be anything, right? It's just so it could be very like a twisted line or something, right? It doesn't have to be a straight line. Okay, so that's what I call a curve or a path. Okay, and the idea here is that because you have just one variable, which is the variable t, right? So if you have one variable, so you're going to obtain a one-dimensional space. So I mean, in general, when I say curve or path, I mean one-dimensional space. It means like there's only one variable, right? Here, we only have one variable, which is t. Okay, so this is only one variable. Okay. Or you can think of like you have like a particle in motion in the space, right? And for each, so each time t corresponds like some position in the space, right? So for example, this is where this is the position of my particle at time t equals to a. And let's say this is the position of my particle at time t equals something between a and b, right? Etc. etc. So each point of this path corresponds to some time t. And the last point would correspond to the time t equals to b, right? That's the position of my particle at time t equals to b. Right? Is there any question, guys, about this definition of path or curve? So again, if you have one parameter, that's what we call a curve or path. So in case of when we're gonna see later in this chapter, chapter 7, we're gonna have like instead of just one variable, we're gonna have like two variables. So in case of two variables, we're gonna have a surface, okay? But for the moment, we have only one variable, which is variable t, and so we're gonna get just a curve or a path in the space. Okay, so some explicit examples. Explicit examples. Okay, first example is when your curve or path is like just like a straight line. Okay, first example, the curve is actually a line. For example, let's say the line, so we are in this space, right? So the line passing through the points, let's just pick a random point, for example, the point 1, -2, 5, for example, right? And so how many lines pass through one point? So if you have one point, how many lines would pass through the point, through one point? Well, there are infinity of lines they could pass through one point, right? I mean, you're in the space. You have some point here, right? So you could have infinity of lines passing through that point, right? This like this line, or it could be this line, or it could be this line, etc., etc. Infinity of lines passing through one point, right? Now, if you want to fix your line, then we have to fix what we call the direction vector, right? This is the direction vector of a line is just a vector which is parallel to the line. So if I decide to to find the line passing through this green point, right? I have this green point, and parallel to the vector. So I have some vector here, a random vector here in the space. I have this vector. Let's call this vector u, or v. Let's call this vector u, for example. Okay. So then there is a unique line which passes through the green point and parallel to this vector u, right? So it's going to be just it has to be this line, for example, right? That would be my line. Okay. So if you are in this space, guys, we have the variables. If you are in this space, to fix your line, you need, let's say, a point and also a direction vector, which is a vector parallel to your line. Okay, so the line passing through this point and with direction vector u, let's say the vector u is the vector 1, 2, 3, for example. Okay, so again, what I mean by the direction vector, this is from Calc 3, okay? But so just to remind you, what I mean by direction vector, that's a vector parallel to your line. So direction vector of a line is a vector which is actually parallel to the line. So once you fix a point and a direction vector, then you can fix your line. There will be a unique line passing through the point and with this given direction vector, right? So how do we find the equation of this line passing through this point and with direction vector u? Well, the idea is, again, this is from Calc 3. Let me just remind you how we find the equation of such line. So the idea is the following. So you have this space. You have your point here. Let's say this is my point, 1, -2, and 5. All right. And then I have my direction vector, u. Let's call this vector here, vector u, which is in our example, 1, 2, 3. Okay, so this is 1, 2, 3. Now, so here's my line. So my line passes through the point 1, 2, 1, -2, 5, and parallel to the vector u. So it should be this line, right? This line here. Okay, so that's my line. Let's call this line the line L. Okay, and I want to find the equation of this line L, right? So the idea is the following. So you take a random point in L. Okay, so your point has some coordinates x, y, z. So this point here has coordinates x, y, z, right? I mean, x, y, z, they are unknown, right? You don't know exactly the value of x, y, z. It's just a point which belongs to your line L, right? Now, I want to find the equation of L. So the idea is you take the vector going from your point 1, -2, 5 to your to the point x, y, z. So you take this vector here, right? This vector. Well, this vector, let's call this vector the vector v. Okay, so this vector v is supposed to be parallel to the vector u, right? Because your vector v lies on the, it's parallel to the line L, so it's also parallel to the vector u, right? So v is parallel to the vector u. Okay. So if v and u are parallel, then remember, guys, if you have two vectors which are parallel, then it means that one vector is a multiple of the other one, right? So like this vector v would be, I don't know, 2 times the vector u, or some constant, some number times the vector u, right? So then v supposed to be equal to some scalar, some number. Let's call this number or scalar t. Okay, t times u. Okay. Now, what are the coordinates of the vector v? So v goes from, v goes from 1, -2, 5 to the point x, y, z. So then v would be just the coordinates of the terminal point minus the coordinates of the initial point, right? So then v is just v is just the vector x minus 1, y minus -2, and then z minus 5, right? So this is, again, this is just coordinates of the terminal point minus the initial point. Okay. And now we are saying that this vector v is supposed to be parallel to the vector u, because u is parallel to the line L. So so then v is a multiple. So this vector x minus 1, y plus 2, z minus 5 is some number, some scalar t times the vector u, which is the vector 1, 2, 3, right? So this is times 1, 2, 3. So again, this is my vector v, and this is my vector u. Okay, and so how do we multiply a number or scalar by a vector? So you multiply each component of the vector by t, right? So it's going to be like x minus 1, y plus 2, z minus 5 equals to t times 1, t times 2, so that will be 2t, and then 3 times t, so that's 3t, right? So in other words, so then the first component here, it's x minus 1. The first component here, it's t. So then x minus 1 is equal to t. Right? So x minus 1 is equal to t. Second component here, it's y plus 2. The second component here is 2t. So that's y plus 2 equals to 2t. And then last component is actually z minus 5 equals to 3t. Right? So if you solve now for x, y, and z, so then x is equal to t plus 1, y is equal to 2t plus 2, and z is equal to 3t plus 5. Okay, and this variable t, it could be any other number, right? Because my vector v is supposed to be a multiple of the vector u, so t could be any number. And actually, we call the variable t a parameter, right? Because it can take any value, any, it could be any real number. So t, so where the parameter t is any real number. And again, guys, you should think of t as like the time, right? So it's like saying when the time t is equal to 0, then I get the point. So then x is equal to 1, y is equal to 2, z is equal to 5, etc. There will be a point in this space, right? So for each time t, okay, so whenever you assign a value for t, you get a different point in this space, right? And here, guys, you can see, so your x is a function of t, your y is also a function of t, and z is a function of t, right? So you get exactly, that's exactly the definition of a path or a curve. So then, so the conclusion is that we get this curve or path. So the line here is the curve gamma of t equals to, so x of t is equal to t plus 1, right? Y of t is equal to 2t plus 2, and z of t is equal to 3t plus 5, right? So this is, again, this is my x of t, this is my y of t, and this is my z of t. Okay, that's exactly the equations of my the equations of my line L, right? So you see, in this case, in this example, our curve is just a straight line, right? This is in this example, the line L, this yellow line, is just a straight line, okay? And that's an example of a curve. Now, is there any question first before the next example? So you see, guys, why a line in the space is, it corresponds to exactly, this is exactly the definition of a curve in the space, right? You get 3 components, and each component is some function of t. Okay, so next example is not a straight line. So example number 2. Example number 2. So my next example is actually a helix. So it's actually given, this helix actually is given by the curve or path gamma of t equals to, let's say, cosine of t, sine of t, and the third component is equal to t, right? With, let's say, with t, so the parameter t is in the interval, t is in the interval 0 to pi. Okay. So what we are saying, guys, here is that so my x of t is equal to cosine of t, y of t is equal to sine of t, and z of t is equal to t. Okay, so for example, when the time t is equal to 0, so when t is 0, oops. So for example, when t is 0, then gamma of 0, so the corresponding point would be cosine of 0, sine of 0, and 0. So that will be the point, cosine of 0, of course, is 1, 0, 0. Okay, so when time t is equal to 0, you get the point 1, 0, 0. When time t is equal to, for example, let's pick another value of t, for example, pi. Okay, so when the time t is equal to pi, then the corresponding point would be, so gamma of pi, that would be cosine of pi, sine of pi, and pi. Cosine of pi is -1, sine of pi is 0, and pi. Okay, so you get another point. So when the time t is equal to pi, you get the point -1, 0, pi, etc. Last point, let's say when the time t is equal to 2 pi, then gamma of 2 pi is equal to cosine of 2 pi sine of 2 pi, and then 2 pi. So that would be the cosine of 2 pi is 1, sine of 2 pi is 0, and then last component is just 2 pi. Okay. And now you can try to graph this, this curve, this helix. So if you try to graph the helix, then you get something which looks like, so this is my x-axis, y-axis, and the z-axis. Okay. So let's say this is here's 1. I'm gonna need probably here's somewhere here, pi. And then let's say the last point is I'm gonna need 2 pi probably somewhere here. Anyway, so for example, when t times t is equal to 0, you get the 0.100. That's my, so this is gamma of 0. Okay. So then if you try to connect, if you try to graph this helix, then you're gonna get something which looks like, something which looks like this here. All right. So this point here, this is, let's say, this is the point, this is gamma of 2 pi, which is 1, 0, 2 pi. Okay. So this would be my helix. Anyway, so here I'm giving this example just to say that the curve, it doesn't have to be like a straight line. It could be anything. It could be some twisted, some twisted line or something, right? But again, the idea is we have only one parameter, which is the parameter t. Okay, so we have sort of like a one-dimensional space, right? All right. Any question about the paths and curves, guys? The space. And as I said, I mean, a path. Well, this is a path or curve. This is an example of path or curve in the space. But of course, you can have also a path or a curve in the plane, right? A planar path. So if so, let me just finish these examples with another remark. Sorry. Example number 3. So a path in the plane or a curve in the plane. Well, in the plane, you're going to have just 2 coordinates, right? X and Y. So that will be some function gamma. So gamma from an interval AB to R2. All right, so then gamma of t would be, x of t and y of t. Okay. So in the plane, you're going to have only, of course, we're going to have only 2 components, right? Because we are in the plane. So in the plane, only 2 components. Okay, so that's why we have only 2 components here, x and y. For example, a path or a curve in the plane would be a circle. So for example, so numerical example. So let's say gamma of t is equal to cosine of t and sine of t, where t is in the interval 0 to pi. Okay. So cosine of t, of course, that would be my x of t. So this is my x of t, that's cosine of t. And y of t is the sine of t. And of course, if you do x squared plus y squared, x squared of t plus y squared of t, that will be equal to, cosine square of t plus sine square of t equals to 1, right? So that will be just a circle of radius 1. So in this example, my path or curve in the plane is just the circle of radius 1. So we have this Again, we have only two coordinates here. This is X, this is Y, and in this case, my curve or path is just the circle of radius 1. Okay. So my path here, or my curve, is just a circle. But again, what you have to keep in mind, guys, is that a path or a curve is it's actually one-dimensional space. So which means basically you take like an interval and some interval, and then you try to twist like your interval. So it's like here I'm taking this interval 0 to pi, right? And then I twisted my interval 0 to pi to get this circle, right? So it's just a one-dimensional space. So this is one-dimensional space. Okay. Any questions? All right, so so that's just a definition of just a reminder definition of a path or a curve in the space or in the plane. Now the question that we're going to try to answer today is how do we integrate? So we have some function f of 3 variables or 2 variables, right? And so the question is, how do we? So suppose, for example, you have a function of 3 variables. So suppose you have some continuous function. Suppose f. Let's say we are in the 3-dimensional space. So we have f is a function of 3 variables. Okay. Of course, continuous function. So continuous function. And so the question is, how do we integrate f along the path or a curve gamma? Okay. And also another question is, what will be the interpretation of such an integral, right? So what's the interpretation of such integral? Okay. So remember, guys, if you have function of 3 variables, we know how to integrate a function of 3 variables over some solid in the space, right? Now, what we are trying to do is to integrate some function of 3 variables along some curve in the space. Okay. So, so let me define this integral of this function f along this curve or path in the space. So, so what we're gonna do, guys? I mean, it's again the same idea. So we have some interval. We have this. So we have this. So path or curve gamma. So gamma is from this interval AB space, right? And gamma of t, we said it's it's x of t, y of t, and z of t. Right. So the idea is the following. So we're gonna do as usual. So we're gonna divide our interval AB. So we have this. This is my interval AB. Okay. So I'm gonna divide AB into subintervals, right? So I'm gonna divide AB into subintervals. Okay, A, let's say, is equal to t subscript 0. Okay, and then I'm going to have another t subscript 1, t subscript 2, etc. And then my b would be t subscript. So my b is t index or subscript n. Okay, so I just divided my interval AB into n subintervals, right? Into n subintervals. Okay, now you can imagine. So if you take the image of these subintervals under the function the gamma, so you're going to have, you have your path here. So here's your path. Right? This is supposed to be gamma of A. Okay, again, A is your T subscript 0, and then you're gonna have, this is gamma of the image of T1, gamma of T1, and then you're gonna have gamma of T2, etc. And then the last point here is a gamma of Tn. Okay. This is, let's say, gamma of T3, etc. Right. So again, I just divided my curve or path in the space into, let's say, sub curves or sub paths, right? And now let's call delta. So let's call this the length of, or the arc length. This arc length here, let's call this arc length here delta S1. Okay. This is delta S2. This is delta S3, etc. So what's the delta S subscript I? That's the arc length of the portion of gamma between, so this delta, so delta S subscript I, that's the arc length. So that's the length of the portion, of the, of gamma between, let's say, gamma of T subscript I minus 1 and gamma of T subscript I. Okay. I mean, if you don't like the indices here, guys, so what I'm saying is that, so for example, delta S1, so for example, delta S1, that will be, the arc length of this portion here. This is my delta S1. It's just the length of this portion here, okay? That's the portion of gamma between gamma of T0, that's A, right? And gamma of T1, right? So this is just so for example, this is just the length of the portion of gamma between gamma T subscript 0, which is A, right? I mean, like my I here would be 1, right? This is my I here. I is 1. So when I say I minus 1, that's 1 minus 1, that's 0. So that's why I get gamma of T0, right? And gamma of T1. Okay. Now, the question is, what's the length of this portion between, let's say, a gamma of T0 and gamma of T1? So now, so the question is, and I mean, you should, I mean, I think you have seen this in Calc 3, but I mean, just again to remind you guys how this works. So now this delta Si is actually can be approximated. So we can approximate. I mean, the thing, guys, is that, I mean, the portion between, let's say, for example, this portion here between gamma of A and gamma of T1, I mean, it's not, this is not a straight line. I mean, this is sort of, it's a curve. I mean, so it's not a straight line. So how do we compute the length of this portion between, let's say, gamma of A and gamma of T1? Well, the idea is, of course, is to try to approximate. So let me just explain here how this works. So, you have this. So we're going to try to zoom in, and this is gamma of, let's say, T1, right? And I want to measure, this portion of gamma between these 2 points, right? The question is, what's the length of this portion, right? And it's not a straight line. That's a problem. So the idea is to try to divide this portion into very small portions. So like here, etc. So now my this is small portions. They are so small that they are kind of like they look like, if you zoom in, they look like a straight line, right? You have like, if they are very small, then they would look like a straight line. And if you have a straight line, okay, then we know how to compute the length of of a line between, or a segment between 2 points, right? We can use Pythagorean theorem, right? So if you have like a right triangle, like if you are in R2, then you would say, well, the difference here. So we have this right triangle. So if you are in R2, we would say this is delta x. This is the difference between the x and the x coordinate, and here this is the difference in the rate of change in the y coordinates. That's delta y, and then the hypotenuse, right? The hypotenuse here would be equal to the square root of delta x squared plus delta y squared. Okay, I just applied the Pythagorean theorem. Now we are not in the plane, we are in the space. So we have 3 coordinates, but still the idea is the same. The idea would be, we have this small portion which looks like a straight line. So I can approximate the length of this very small portion with using the Pythagorean theorem. So that would be square root of delta x squared plus delta y squared plus delta z squared. So again, guys, when I say delta x or delta y, delta z, that's the difference between, the x coordinates. It's like saying delta x is like x subscript I or subscript k minus x subscript k minus 1, right? That's the rate of change of your x, the variable x. Delta y is the rate of change of your variable y, etc., right? So so I can approximate my delta si, the arc length, the portion of gamma between gamma of ti minus 1 and gamma of ti, with using this Pythagorean theorem. So then my delta si can be approximated, the sum, right? I divided my I divided my arc length into very small portions, right? So that would be a sum of square root. You have delta of x. So here, of course, your x depends on the parameter t, right? X, it's x of t. Y, because again, because we have a path or curve, right? So the first coordinate is x of t. This is y of t and z of t. Okay, so this is supposed to be delta of x of t. Let's say t subscript k. This is a square plus delta y of, let's say, t subscript k. There's a square here, and then there's z, the square of tk. Right, so the sum, let's say, over k here. So k going from 1 to n. Okay, so I just divided my arc length into n very small portions, right? Now, this is just an approximation with the very small portions of your curve, right? And so the idea, of course, is to let n go to infinity, right? So then delta Si is actually equal to the limit. So as n gets very large, so you're gonna have very, very small, portions, and you're gonna get better approximation, right? And actually, when n goes to infinity, that will be equal exactly to your arc length. Okay, sum over k here. So we have this square root, partial delta x, y, and delta z square, of course, right? This is just a Pythagorean theorem. Anyway, so once we have this, so this reminds you actually definition of integral. When we have this Riemann sum, you have this limit and going to infinity of your Riemann sum, right? So that's actually equal. So this is the definition of integral, the function of, let's say, a function of single variable. So this is, so that will be the integral over your portion. This is a portion of gamma between, let's say, gamma of t I minus 1 and gamma of t I. Okay. And you have the square root. Okay. Now, this delta x or delta y or delta z, when you take the limit and going to infinity, so this rate of change, the rate of change of your variable x or variable y or variable z, when n goes to infinity, this delta x by definition is going to be dx, right? And delta y is going to be dy, and delta z is going to be dz, right? That's the exact definition of your differentials, right? So this is actually dx as a function of t, of course, square, plus dy of t square plus dz of t square, right? So again, guys, delta x goes to dx, when n goes to infinity, so when n goes to infinity, delta y becomes dy and delta z becomes dz. All right. Now, so what's exactly dx of t? Well, I mean, dx of t, so d of x of t, this is actually, you can write it like dx of t over dt dt, right? So I just, it's like saying I multiply and I divide it by the same thing here, which is dt, right? So in other words, but I mean, dx dt, that's the exact definition of x prime of t. So this is actually equal x prime of t dt. All right. So you see, guys, dx of t, x is a function of t. You can write it as it's just x prime of t dt, right? Now, you can do the same thing with the y and the z, of course. So then this square root, so we have this integral. So this portion of gamma between, gamma of t index I minus 1 and gamma of t index I. So it's like saying your t is going from I minus 1 to t index I. All right. And then you have the square root of, so dx of t, you can write like x prime of t dt, right? So it's like saying you have like x prime of t dt square, y prime of t dt square plus z prime of t, dt square. Okay, and then of course you can factor, well, you have dt square, so you can factor out dt square, and it's a square root, so that will be dt outside the square root, right? So this is just equal. So this is, again, this is the length, or the arc length of the portion of gamma between gamma of ti minus 1 and gamma of ti, right? So this is equal to this integral single variable between these ti minus 1 and ti of, so here it's going to be square root of x prime of t plus y prime of t plus z prime of t, and then there's this dt outside, right? Again, the dt, it's because you see here you have this dt square, dt square, dt square. You factor out dt square, and then because of the square root, it's going to be just dt, right? So that's, again, that's the arc length of the portion of gamma between, that's between gamma of ti minus 1 and ti, gamma of ti. Now, again, this is just the arc length, So I'm gonna come back to my function f. Remember, I have this function f of 3 variables, and the goal was to, integrate f over along my path or my curve, right? So now back to the function f. Function of 3 variables. Right. And so we're going to integrate f along the curve gamma of t. Right. So we know exactly the arc length. Let me just remind you here the picture. So we have this AB. Here 3 coordinates, x, y, and z. So we have this curve gamma, right? This is gamma of t. So this is, for example, we said this is gamma A, and this is gamma B, and we said we divide our curve into small portions here. Okay, so this is a gamma of t1, this is gamma of t2, etc. This is gamma of tn. Anyway, so and we said, so the arc length of this portion, delta s1, etc. So we know exactly the formula for the arc length. So now we're gonna consider. So we consider the Riemann sum. Okay. Again, I divided my interval here, AB, into n subintervals. This is a T1, this is T2, etc. So f, sum of f of gamma of Ti times the arc length of the portion between gamma of Ti minus 1 and gamma of Ti. So delta Si. Okay. I, of course, going from 1 to n. Okay. Now, when you take the limit, so again, guys, this delta Si, this is the arc length of this portion between these 2 points of the curve, right? This is my delta Si, right? And I'm multiplying this delta Si by this function f here. So then the definition, so we can define the scalar line integral line integral of f along the path or the curve gamma of t as so first the notation is the following. So it's the integral of f, okay, over gamma, okay, and here you have ds. So the ds, guys, that's the length element of gamma, right? This is the length, the ds, that's the length element of gamma, right? Your curve gamma. You're integrating along gamma. Okay, and here's your function f. Okay. Why it's called the scalar? We're gonna see later. We're gonna have also a vector, like a vector version of this definition. But here we it's defined as it's called the scalar line integral. It's a scalar because this function f is this function f is a function of the variables, but f is a function of the variables, right? But the result would be just one number, right? I mean, for example, f of xyz is equal to, I don't know. So for example, f of xyz is equal to, x times y times z, right? So my function f is from R3. It takes three variables, but the result is just one number, right? And because it's just one number, it's called a scalar. Okay. Okay, you get when you evaluate your function f, you get just one number. So that's why it's called here a scalar. It's a scalar line integral, right? It's because f is seen as a scalar. So here, f is seen as a scalar. And again, what do I mean by a scalar? A scalar, it means just a number, a real number, let's say, okay? A scalar, this is just a real number. Okay, on Thursday, so we're gonna see another definition of line integrals along the curve, but not of a scalar function. We're gonna see how to integrate a vector function along a curve, right? So in this case, my function f is not a vector; it's just it's a scalar function. It means that the result is just a number, not a vector, right? That's a notation. This is actually equal to. So this would be equal to. I'm gonna need some space here. Let's just erase this, I guess. So this is equal to the integral from a to b, right? So we have this f of gamma t. So f of gamma t. Okay. And then there is this delta s, right? So when you take the limit, this delta s becomes this ds, and that's actually equal to, this ds is just, I just explained here that this ds would be, this square root of x prime of t plus y prime of t, etc. dt, right? That's this is the length of gamma prime of t, right? This is the length of gamma prime of t. Okay, so in this integral, we're gonna have here, we're gonna have, this is the notation for the length of gamma prime of t. dt. So what's this length of gamma prime of t? That's equal to, let me just finish the definition here. So this is supposed to be equal to the limit, of course, n going to infinity of my Riemann sum, right? I going from 1 to n, and say f of gamma of ti delta si, right? Where, so this is just a square root of, x prime of t, square of x prime of t plus the square of y prime of t, y prime t square plus z prime t square. Okay. So before the numerical examples, guys, so I'm gonna just give you like one interpretation, one possible interpretation of this scalar line integral. So one possible interpretation would be just, so if you integrate the constant function 1, so one possible interpretation. So if this function f is just if f of x, y, z is equal to 1, the constant function 1, right? Then this scalar line integral, so that will be 1 here, ds over gamma, along gamma. Okay, so that will be actually equal to the arc length of gamma. Okay, which is, the integral from a to b, the length of gamma prime of t dt. Okay. So what I'm saying here, guys, is that if you integrate the constant function 1 along gamma, then what you get is the length of your curve gamma, right? So, I mean, this is not really bad. I mean, it's, you have 3 coordinates x, y, z. You have some curve. This is your curve gamma. So this is gamma of a. This is gamma of b, and so this is your curve gamma. Again, gamma is not a straight line. Okay, it could be anything. Gamma, it's just it's a curve, so it's just one-dimensional space. It could be very, twisted. It's not straight, necessarily straight. And what I'm saying is that the length of gamma length of this curve gamma is actually equal to this, to the integral of 1 along the curve gamma. Okay, I mean, this is kind of powerful. I mean, it's not really bad. I mean, it's not like saying you have a straight line and you are using like Pythagorean theorem, right? If you have like a straight line, well, I can just say, well, I can use, Pythagorean theorem, and I can find the hypotenuse here, right? If it was a straight line, but this is not a straight line. It's just some random path. Any question, guys? Okay, so let me just give you one example with the steps. I'm going to show you how to evaluate these scalar line integrals, and then I'm going to give you an exercise. All right. So let's see. Example. Yeah, let's come back to this example of helix. So numerical example. So let's say you have gamma from 0 to pi to R3. Going to be this helix. So gamma of t is equal to cosine of t, sine of t, t. Okay, and let's say you have some function f of 3 variables. So f of x, y, z let's say it's xy, for example, plus z. Okay, just some function f of three variables, and so your curve is this helix, and you have this function f, and you want to evaluate, let's say f, the integral of f, the scalar line integral f along this curve gamma, right? So the question is, evaluate the integral or scalar line integral of f along gamma. Okay. So first step, you have to compute the length of the derivative of gamma. So step one. So we have to find the length of this gamma prime of t. Okay, because we're gonna need it. Inside the integral, we're gonna need this length of gamma prime of t, right? So, gamma of t is cosine of t, sine of t, and t, right? Then gamma prime of t. So we just take the derivative of each component. So derivative of cosine is minus sine of t, of course. Derivative with respect to t. Derivative of sine of t is cosine of t, and derivative cosine of t here, and derivative of t is just one, right? So we are taking derivative with respect to t. That's your gamma prime t. Now you're going to take the length of gamma prime of t. So the length of gamma prime of t, that will be square root the sum of the squares of the components. So it's minus sine of t square plus cosine of t square plus 1 square. So that will be square root of sine square of t plus cosine square of t plus 1. Sine square plus cosine square, that's 1, of course. So that's square root of 1 plus 1. So that's just square root of 2. Okay, that's the first step. We got the length of gamma prime of t. Step 2. We need to find f of gamma of t. Right. So guys, gamma of t is again it's just this cosine of t, sine of t, t. Right. So in other words, x. So x of t is, or x is cosine of t. Your y component, y coordinate, y of t is equal to sine of t, and your z of t is equal to t, right? Now, f of x, y, z, we know that f of, this is given in the problem, so f of x, y, z, we said it's x, y plus z, okay? So then that will be equal to, your x is cosine, your y is this sine of t, and then plus z, your z is equal to t, right? So that will be cosine of t times sine of t plus z, which is t plus t. Okay, so that will be, this is f of gamma t. Okay. So I just expressed f in terms of t. And then the last step, we can now integrate. Step 3, we have all the ingredients, to integrate f along the curve gamma. So this is my step number 3. So the integral of f along the curve gamma is equal to, so by definition, let me just write down definition, it's f of gamma t, the length of gamma prime of t, dt, right? So t, your t is, in the interval 0 to pi, right? Here's t. T belongs to the interval 0 to pi. So here, so we're going to have 0 to pi because t is in the interval 0 to pi. Okay. Now, we know the length of gamma prime of t. This is from the first step. This is from step 1. We know the expression of f in terms of t along the curve gamma. So this is from the step number 2. All right. So that will be the integral from 0 to pi. So f of gamma t is just so this is from the step number 2. So f of gamma t is just the cosine of t times sine of t plus t. So here's my cosine of t times sine of t plus t. Okay, so this is my f of gamma t. Now, the length of gamma prime of t, that's from the first step. So we said, oops. So from the first step, we said the length of gamma prime of t is square root of 2. So here, we're going to have times, so this is multiplied by square root of 2 dt, right? The square root of 2, this is just the length of gamma prime of t. Okay. So, well, so that'll be equal to, so first we have to integrate. I mean, we can, of course, put the square root of 2 outside the integral. It's just a constant. So from 0 to pi, cosine t sine t plus t dt. First, you can integrate this cosine of t sine of t. I mean, you can use a substitution if you want. Let's say, for example, u is equal to sine of t or something, or u is cosine of t. Anyway, so I mean, derivative of sine is cosine, so that would be just the square root of, sine square of t over 2, right? From 0 to 2 pi, and then plus the derivative integral of t is just, of course, t squared over 2 from 0 to 2 pi. Okay. Anyway, so sine of 2 pi is 0, sine of 0 is 0. So this thing here is just 0. And then we have this t squared over 2. So we have this, so t is equal to 2 pi. So this is just a square root. So this is 2 pi squared over 2. And so that would be 4 pi over 2. That would be 2 pi times square root of 2. So that's just a 2 square root of 2 pi squared. Okay. Again, this sign here is 0 because sine of 2 pi is 0 and sine of 0 is 0, right? Any question, guys? All right, so here's an exercise. Well, before the exercise, guys, I just said as a remark, I mean, your curve or your path gamma, it could be a path in the plane, right? So just let me quickly make an example. So in case of, this integral of f along the curve gamma can be also defined for gamma, which is a path or a curve in the plane. Okay. So, for example, numerical example. So here's a quick example. So let's say, example. let's say gamma of t is equal to 2t and t. T, let's say, is in the interval, for example, 0, 3. Okay, so you see in this case, your curve gamma is actually, so it has two components, right? So if it has two components, it means that's a curve in the plane. It's not in the space, right? So you have just two coordinates here, x and y, and your curve gamma could be, you know, any path here in the plane, right? You can take, so if you are in the plane, you have two components in the plane. You can take a function of two variables. So let's say f of x, y. Let's say it's y minus x. Okay. And so you want to evaluate again f along gamma. Okay. So then you do the same thing, but just with two variables instead of three variables, right? So it's you know, first you're gonna need the length of gamma prime. Okay, so you know, gamma prime of t is just equal to, so gamma of t is 2t, right? So gamma prime of t is just 2, 1. So then the length of gamma prime, it's square root of 2 squared plus 1 squared. That's the square root of 5. All right, and then f of gamma t, that will be equal to, I mean, f of xy is y minus x, right? So it's gamma yt minus x of t. Well, y of t is is equal to t, and x of t is equal to 2t, right? So then, so this y of t minus x of t, that will be equal to t minus 2t, and that will be equal to minus t. Okay, so then just so then this integral of f along the curve gamma is actually equal to, so your function f, so let me write down here for you the definition. So it's f of gamma of t, the length of gamma prime of t, dt. T is in the interval, you know, 0, 3, right? We said here in the problem, t is in the interval 0, 3, right? So we're going to integrate from 0 to 3. So here it's integral from 0 to 3. So that will be integral from 0 to 3. The function f of gamma t is just minus t. So here's minus t times, and the length of gamma prime of t is square root of 5. So it's times square root of 5 dt. And then you can easily compute this integral, right? Anyway, so this is just an example when you have, you know, your path gamma is in the plane, not in the space. Okay, guys, I don't know if there's any question. Otherwise, so here's an exercise for you. So, of course, the goal of the exercise would be to evaluate our scalar line integrals. So, exercise. So number one, so it's going to be a curve in this space. So let's say gamma of t. Oops. Can I use this color black here? Okay, so oops. Gamma of t is equal to, let's say, exponential of 2t times cosine of 3t. Second component is the same exponential of 2t times sine of 3t. And last component is just exponential of 2t. All right, that's my curve or path gamma in your space, right? Where t, of course, the variable t is the interval AB, belongs to the interval. Let's say t is between 0 and 5. Again, this is a symbol here, guys. This means belongs, right? So t belongs to the interval 0, 5. So that's my path gamma, my function f, let's say my function f of x, y, z is equal to, let's say, z over x squared plus y squared. Okay, and the question, of course, would be to evaluate the scalar line integral, so the integral of f along the curve gamma. Second exercise, so this is a case of a path or curve in the space. Now here's an exercise with a gamma in the plane. So number 2, so let's say gamma of t is equal, so gamma of t is going to be a circle, so it's just a cosine of t, sine of t, t in the interval, let's say 0 to pi, right? And my function f is equal to x plus 2y. And so let's take, instead of the interval 0 to pi, let's take not the whole circle. I'm going to just take the half of a circle. So t is in interval 0 pi. Okay, not 2 pi, but just pi, right? And the question is to evaluate this function f along this curve gamma. Right. Okay, guys, I'm gonna give you like 5-10 minutes. Well, yeah, let's say 5-10 minutes to think about this exercise. I hope you can see everything here. Yes. So actually, with this exercise, we're gonna finish. We are done with this section 7.1. So I guess Thursday we can start section 7.2. And as I said, both sections are not. They are not in the test. They are not included in the test. So the test is gonna be just about the chapter 5 and 6, right? So this is not. Again, this is not. It's not included in the test, right? This is not in the test. And of course, guys, if you have any question about the review sheet, just send me an email. So my plan, of course, as I said, we're gonna have a review next Tuesday. If you have any question about any problem in the homeworks or the review sheet, just let me know. And if you don't have any questions, then I'm gonna just try to solve the problems in the, in the review sheet. Anicia, by the way, I guess we need to talk this week about the honors project. I mean, we can meet, let's say, um, um, I mean, tomorrow or Thursday or Friday. I mean, we can discuss the project and all you have to do in this project. Um, um, I mean, I will probably I will send you an email, right? We can talk on on Zoom or.
Okay.
Mhm. So what's your plan, Anicia, after BCC? Um, do you want to go to one of the CUNY colleges or?
I'm a concerned. I don't know where as yet. I applied to both CUNY and out of state.
Okay, okay. Oh yeah, and by the way, you have, I guess, to submit this form online. But all you need, actually, is I think you need the title of the project. So, I mean, my suggestion is that the title would be, as I said yesterday in the email. Let's say the title would be like the Carton structural equations. Um, uh, and I think that's all you need to submit the form. Um, I don't think you need a description of the project, just a title, I
Yes,
guess.
only the title.
Yeah, title, right? Okay, perfect. So I guess so. I mean, if we're interested, then you can just use the structural Carton equations as a title.
Okay.
Mhm. And I have also to submit the form, right? I guess I will check it. But I think we have to start like as soon as possible, because this could be like kind of a long, but not long, but it could take a lot of time actually to understand. There's a lot of lot of definitions, but still there's always a nice like a geometric interpretation behind this theorem. So it's not like something which is very abstract. I mean, but anyway, but
Okay.
we need to talk some point this week, because
Hmm.
we need to start like as soon as possible.
Yes.
Mhm, sure. Um, all right. I don't know if you guys have a trouble with this exercise. I mean, I guess we have like 5 minutes. I I can probably solve the first problem. I mean, both are just similar. It's not. I don't think it's really hard once if you know the formula, of course. Um, All right, guys. We have just like a few minutes, so I'm gonna just go over the first problem, I guess. I don't know if you tried one of these problems, but let's just do it. Let's do the first one. Okay, so number one. So first step, we said step one. So we have to find the length of gamma prime of t. All right, so I mean, gamma of t is this exponential. Sine of 3t, exponential sine of 3t, and then exponential of 2t. So then derivative, gamma prime of t. So that would be the exponential. Well, of course, this is a product, so we need to use a product rule. So the derivative of exponential of 2t, that would be 2 exponential of 2t cosine of 3t. Derivative plus, derivative of cosine is minus sign, so it's minus because there's a 3 inside the cosine, so there'll be minus 3 exponential of 2t sine of 3t. And then next, we have again the product. So derivative of exponential of 2t, that's 2 exponential of 2t sine of 3t. And then derivative of sine is cosine, so that's plus 3 exponential cosine of 3t. And derivative of exponential of 2t is just 2 exponential of 2t. Now, if you take the length, gamma prime of t, so that'll be like square root, this 2 exponential 2t cosine of 3t minus this 3 sine of exponential of 2t sine of 3t square plus, well, this is going to be a long square root. So plus another 2 exponential 2t sine of 3t plus this time 3 exponential 2t cosine. Of course, here there's a missing parenthesis. Cosine of 3t square, and then plus this 2 exponential of 2t, and then there's this square, of course. All right, guys. Anyway, so you have to, distribute, and then there will be a constellation here. It's gonna be like, take the square, so it's gonna be like 4 exponential of 4t, cosine square of 3t, plus 9 exponential 4t sine square of 3t minus 3 times 2 times 2, that will be 12 exponential 4t cosine of 3t sine of 3t. Okay, this is just first square plus the next square, 4 exponential 4t. Let me just write down, sorry guys, I'm gonna just write down here this square, and then I'm gonna stop. Okay, so just so this is, sorry, here this is sine square 3t plus 9 exponential 4t cosine square 3t plus 12 exponential 4t cosine 3t sine 3t, and then plus this 4 exponential 4t. So you can see here, guys, there's going to be some oscillations. So here it's minus 12 plus 12, the same thing. And then here you have cosine square plus sine square. So this thing here is going to be just, so it's going to be square root. So you can factor out 4 exponential of 4t. So that's 4 exponential 4t times 1. Plus here, you can factor out 9 exponential 4t. So that will be plus 9 exponential 4t. And there's this 4 here. exponential 4t. Anyway, so in total, we're going to have 4 plus 9, 13, plus 4. So that will be 17 exponential 4t, right? So that will be square root of 17 times exponential of 2t. Okay, so that will be the length of gamma prime of t. All right, so then, and then you have to find your function f. Let me just write quickly, very quickly. Sorry, this. So f of xt, yt, zt. So it's going to be exponential of 2t over x squared plus y squared. So that would be exponential of 4t. So here f would be 1 over exponential of 2t. All right, so then you have everything to evaluate your integral. So you're going to have this integral from 0 to 5, the exponential of minus 2t, right? This is exponential of minus 2t times the length, which is of gamma prime of t, which is square root of 17 exponential of 2t dt. So here the exponential, they're going to cancel out. So it's just the square root of 17 between 0 and 5. So that's the answer would be 5 square root of 17. And that should be fine answer. Anyway, guys, so I'm going to stop here. And so I guess I will see you on Thursday. All right, so Anicia, I will send you an email later, okay?
Okay, Professor.
Okay, thank you guys. Thank you, David. Take care. I will see you on Thursday.
Bye.
Bye.